and presenting us your work,
Yep.
which is going to be about dual reduction in elementary games with senders and receivers, which is a game theory paper about which we are very happy, which I guess will be something like about the refinement of communication. We are refining, not mistaken. The floor is for the the stage is yours.
I may speak?
Yes.
We're ready to go? Thank you. I'm very, very glad to be able to participate remotely, and when I can't come to Hungary this summer, in this mechanism design conference, where one of the major themes of this conference is to honor Vince Crawford, and this paper is about taking a paper of mine from 1997 and extending it to the framework of sender and receiver games, which Vince Crawford and Joel Sobel really initiated for us in their great classic paper from the 1980s. I think, let me say, as people are coming about mechanism design, I think the heart of the mechanism design problem is the understanding of incentive constraints, the incentive constraints that restrict the set of feasible coordination mechanisms. And for a long time, I've thought, for over 40 years, I thought that there should be something we could do useful with the Lagrange multipliers or dual prices of incentive constraints. And to truly understand the problem, we should understand them. This paper is in some ways, I think, defines a frontier for how we can understand the deep structure of mechanism design, of game problems, of coordination problems, using analysis of the dual prices of these incentive constraints. And in some ways, we'll see that it may shed a new light, perhaps, on the whole problem of refinement of equilibrium by posing it in the framework of communication mechanisms, coordination mechanisms. So I've got a review, I think, my paper from 1997 on dual reduction in elementary games. I hope perhaps, if I'm lucky, perhaps a few in the audience may have studied it at some point, but it hasn't found a lot of applications. And yet I hope you'll agree, the mathematics is so promising, and the insights that it gives into games so deep that there should be applications to be developed in the future. But as I say, that paper was written in the context of strategic form games. Strategic form games sound general, but actually, when you're in the mechanism design framework and you're using the revelation principle is fundamentally incompatible with the strategic normalization principle on which game theory was founded. You have to pick one or the other, and here we're picking the revelation principle. So let me and I will talk about sender-receiver games, not full Bayesian games, and that's a good question we might talk about at the end if there's time for questions. So let me develop the framework and start developing the results, because there's a lot to do. A finite sender-receiver game. I hope my slides are visible. I'm highlighting. I don't know if it's visible to see that I'm trying to highlight, or my cursor is going over near the sender-receiver game is defined gamma as having I'm going to say the players are of two types, of two categories: the senders, who have private information described by their types, and the receivers, who have actions. Won't have full in a full Bayesian game. Some players would have both, but I'm not going to go that far today, because we'll see enough. We'll learn a great deal just by having the sender-receiver framework about both moral hazard incentive constraints that were covered in the previous paper and the adverse selection or informational incentive constraints that are introduced in the sender-receiver game. So I and J are the players. The union of our two disjoint sets of players. I are the players who are senders, and capital J is the set of receivers who have actions. The set of types for player I is in sender I is denoted by capital T sub I, capital C sub I. Capital C sub J is the set of possible actions for player J who is in the set of receivers. Little p denotes the probability distribution over the profiles of types. That's the prior distribution over types. And For any k who could be either a sender or a receiver, the utility function of player k can depend on the profile of all the actions and all the types of everybody. And u sub k, little u sub k denotes the set of denotes the utility function. Those sets I and j are finite disjoint sets, non-empty finite disjoint sets, and ti and cj are also non-empty finite sets for today. Everything is all sets are finite today. And I introduced some basic notation. So a direct coordination mechanism. This should be very straightforward. And I'll in the middle of the slide, I'll let little capital U sub j for receiver j, or for any player j. No, little u sub for any receiver j. U sub j of mu. Let's see, what's a mechanism? Mechanism is any mu that's a function from the profiles of types into probability distributions of actions. So mu is going to, I can see there's a mu of c given t. C is a profile, little c is a profile of actions, little t is a profile of types, and mu is the probability that the profile of actions would be recommended to the receivers if the senders reported that their types were as in the profile of types were as in t. I'm going to assume throughout that all communication about in implementing a mechanism is confidential. That is to say, first, each sender confidentially reports his or her own type to the mediator. Then the mediator runs the mechanism mu randomization to select a profile of recommendations to the receivers, and with mu of c given t being the probability, and then cj is confidentially recommended to receiver j. So the expected payoff to player j when he's told to do cj in the mechanism mu is the sum over all possible types that multiply their probabilities, sum over all possible actions for everybody else, take the probability of that. And I'm just realizing everything here is probability discounted because we really should be dividing by the prior probability of player j getting recommendations cj. But I'm going to these are not actually, so I back up. These capital U numbers in the middle of the page here, they're not conditional expected utilities. They're conditional expected utilities multiplied by the prior probability of the event that has been observed. So I could call them probability discounted expected utilities. They're proportional to the expected utilities, and they're linear. That's the important thing. They're linear in mu. So we're not going to divide through by any prior probabilities because we don't want to. So the portion of the prior expected utility of player j that comes from his being recommended cj, if he's honest and if everybody's honest and obedient, is described by uj of mu cj, and u hat of j mu dj cj is the portion of the same portion of the expected utility contribution if everybody is being honest and obedient to the mediator, but player j is deviating when he's told to do cj. Player j deviates and chooses dj instead, and everything's the same in the u hat j, except that the utility function for player j depends on his actual dj. Similarly, the portion of player i's ex ante expected payoff before he learned his type that comes from her or his or her being of type ti when everybody's being honest and obedient is you sum over the types of everybody else. T minus I is the types of everybody else. Take the probability of the joint distribution of this joint profile of types. Then what does the mechanism do, and what does player I get when everyone's honest and obedient? And if player I were truly if player I planned, if I'm of type Ti, I'll do Si. Then the share of the ex ante, the terms in the ex ante expected payoff that come from that the event that player I is told to be Ti is actually type Ti, but claims to be Si, are the same as before, except that the mechanism is choosing the Cs based on the Si, not the true Ti. But the payoffs, of course, depend on the true Ti. So those are the usual things in mechanism design. And incentive compatibility says that mu is incentive compatible if and only if honesty and obedience, but honesty by all senders and obedience by all receivers forms a Nash equilibrium, and that requires that that no receiver J can expect to do better by by deviating to DJ in the event that he's told to do CJ, and no sender I can expect to do better by reporting type SI when the type is TI. And also, these mu's must be probabilities, which means that the mu of C given T's are non-negative, and for every T, the sum over all C's of mu of C given T sums to 1. Those are the constraints that define the incentive-compatible mechanism. Now, the first new definition. A game is elementary. An elementary game. This is a game where there exists at least one mechanism, I'll call it mu star, such that it's an incentive-compatible mechanism, and all the incentive constraints are strict. By the way, that implies that every action gets recommended with positive probability, and because these capital U things are ex ante are portions of ex ante expected payoffs that come from these events of having CJ recommended or having type TI. So we're going to need that all types have positive probability, and we certainly are going to assume that all types have positive probability. In fact, we might as well assume that I will at some point assume that all P of T are positive. That is to say that strictly positive. That is to say that the probability distribution P has full support. Anyway, an elementary game is one where all non-trivial incentive constraints can be satisfied strictly. I can't say all incentive constraints are satisfied strictly, because in my quantification I included the trivial incentive constraints where DJ equals CJ or TI equals SI, where you're reporting you're deviating from your type to report your actual type. That's formally included among the incentive constraints. Those are the trivial ones, and those of course are always satisfied as equalities, trivially. But if all the non-trivial incentive constraints can be satisfied strictly, then we say we have an elementary game. What I want you to see, first and foremost, is that if gamma is an elementary game, you might think there aren't very many elementary games, or that they're rare. They're actually, we're going to show that in some sense that maybe almost anything can be modeled by an elementary game in a certain way. That will be the bottom line. But if the first thing to say is, if gamma is an elementary game, then almost all incentive constraints satisfy all non-trivial incentive constraints strictly. Why? Because if you have an incentive-compatible mechanism mu that does not, and then you have that one mu star you found which satisfies them all strictly, take any arbitrarily small positive epsilon weight of mu star and 1 minus epsilon weight on mu, and you've got a mechanism that's almost the same as mu. You're just with an epsilon probability deviating to mu. The mediator is with an epsilon probability deviating to mu star. But now in this mixture, which is very close to mu, all incentive constraints are strict because they are strict in mu star, and we're adding a strictly satisfied incentive constraint averaged with a weakly satisfied averages to strictly. So almost all, the whole relative interior of the incentive compatible mechanisms, almost all incentive compatible mechanisms satisfy all incentive constraints strictly in an elementary game. So there is, in that sense, there is no perfection problem. All the incentive constraints are strict. Remember, our Nash equilibria are themselves a subset of the incentive compatible mechanisms. The Nash equilibria of any game with communication. So now let's start doing dual analysis. Let's learn to do something with the dual variables. Well, what do? You write down. I'm of the old generation where we used to study and teach linear programming all the time, and it's good for you. Let me say, I'm not sure what Well, anyway, so let's write down a linear programming problem. All of those incentive constraints, I'll go back to are linear in the vector of probabilities that the mu mechanism is, and the probability constraints are obviously linear. So we could just write down maximize 0 subject to those constraints, and you've got a linear programming problem. Well, I did something a little different. What I did was, in order to guarantee, we know because Nash equilibria exists, Nash proved that the set of incentive compatible mechanisms is nonempty. But let's just write down a linear programming problem, which is obviously feasible, has some feasible solutions, but the optimal solutions will be the incentive compatible mechanisms. So that's what I call the primal linear programming problem. What I'm doing is for each action of each player of each receiver J, and for each type Ti of each sender I, we're going to add in what we just call them artificial variables that or cheating variables that if you made them positive, you could always satisfy, and made everything else zero, you could always satisfy all the constraints, the incentive constraints. So I want those to be zero, but if you made pi j of Cj in the strictly positive large enough, you could always satisfy that. Let's see, we've got the sum over all type profiles T and action profiles C other than the player J of how much player J does better by being honest and obedient than by deviating to action J when CJ is recommended. You sum that, and that should be non-negative. We'll add in a pi J of CJ and say that sum should be non-negative. The pi are going to be unrestricted. The mu's have to be greater than or equal to zero. That's because they come from a probability. They're probabilities. All the components of mu are non-negative. That's something you can say in linear programming. But the pi's are not unrestricted. Notice, by the way, because I'm quantifying overall Cj and Dj, that includes Dj equals Cj, in which case the summation term in this first primal constraint is trivially zero, and therefore the first primal constraint includes a constraint that says pi j of Cj is greater than or equal to zero, even though I called it a free variable. One of the constraints says it's non-negative. Similarly, the pi of Ti, when you look at the Si equals Ti constraint for type Ti of sender I, the pi of Ti is guaranteed to be non-negative because of the trivial incentive constraint of Ti imitating himself, and so now this constraint says a non-negative number plus the expected gains from misreporting your type as Si when it's really Ti should be non-negative, or sort of plus the advantage of saying Ti rather than misreporting it as Si has to be non-negative. And then we're going to try to minimize these non-negative numbers, and of course the optimal solution will have them zero, because we know that incentive compatible mechanisms do exist. And of course there's also the linear constraints that the probabilities have to sum to one. So I'm going to call alpha on the right. I've indicated in red on this slide the dual variables for each of these primal constraints. The dual variable for receiver J not wanting to do DJ when he's told to do CJ, that I'll call alpha J of DJ given CJ. I'll call alpha I of SI given TI, and the vertical slash instead of a comma reminds you that the thing to the right is the given. Says that given that your type is really TI, you shouldn't want to misreport SI. And then the probability constraints, they have Lagrange multipliers or dual variables, and there's one for each profile types. I'll call that beta of T. So those are the variables of my dual problem. The solutions to the linear program, this LP, are the set of incentive compatible mechanisms. Because of Nash's theorem, we know the optimal value is zero and has all the pi's equal to zero. And I note here again, as I said, that the trivial constraints imply that although I called pi a free variable, it's implicitly non-negative because of the trivial constraints. So now the dual problem we choose non-negative alphas and betas free variables. Because the dual variables for the pi's are free variables, and I write them down as equalities. The sum, and they basically those free variables basically say that the sum over all DJ of alpha J of DJ given CJ is equal to 1. So these are these Lagrange multipliers or dual variables look like a Markov chain. The alphas look like a Markov chain on the respective, or look like a group of Markov chains. Each alpha I is a Markov chain, is a set of non-negative, summing to 1 for each Ti, they sum to 1. So it looks like a Markov chain on the types of player I, and each alpha J gives us what looks like a Markov chain on the actions of receiver J. And then the dual constraints for the mu's for each of the probabilities in the mechanism basically say, well, it's a complicated thing because the mu's appear every you turn the crank. Let me take that long, messy constraint, and it has a beta T because each mu component appears in one beta in its respective beta T constraint, and then it appears in lots of incentive constraints. This constraint in the middle of the slide says that beta of T is less than or equal to the negative of this huge expression. The negative, the opposite of this huge expression, is what I'll call dct alpha. It depends on there's one of these for each profile of action C, for each profile of types little t, and of course it depends on the dual variables alpha. And basically, this in the lower third of the slide, I talk about this capital D of CT alpha is the alpha deviation value at C and T. What is it? It's just taking all the mu terms in the dual and multiplying them by -1 so as to get them on the right-hand side, and say beta t has to be less than or equal to this dct alpha. But what is this? This is, you're looking at each of the receivers. We've got a particular profile of actions, a particular profile of types, and we ask, how much does each player, it's the deviation, taking unilateral deviations for each receiver from a CJ to a DJ, and asking how much would he gain by that deviation and multiplying it by its dual variable. Similarly, we're going to get, for the receivers, it's a little more complicated, but basically what you've got, you're subtracting two terms. The positive term is coming from, we're talking about deviation values. It has probabilities and utilities for when the player is of type SI pretending to be TI, and then it has a negative term, which is for type TI being himself, but each weighted by we take the constraint of SIs that could be tempted, that have a positive Lagrange multiplier. We'll consider a constraint with a positive alpha of TI given SI. That's an SI that's tempted, that has a positive Lagrange multiplier for its temptation to claim to be TI. How much does player SI get when he pretends to be TI from this particular C, and everybody else is being honest? And then for every type TI that could be claiming to be SI, we're subtracting off the contribution to paying him not to do it, which is the actual payoff when the player is honest. So these are deviation values. They're how much doing C in type T contributes to the aggregate temptations of players to unilaterally deviate, where each of those unilateral deviations is being weighted by its respective Lagrange multiplier. And we understand these DCT alphas as deviation values, then this says that the optimal solution to the beta, you're trying to the dual problem is a maximum because the primal was a minimum. So we turn the crank of duality and linear programming. It basically says we're going to maximize the beta. The optimal solution has to be, for any alpha, that you're going to choose the beta to be the smallest of the DCT alphas. The beta depends on T, so you minimize over all C, action profile C, the aggregate deviation file. Find the action profile that has the smallest aggregate alpha deviation value, alpha aggregated deviation value for the profile of types T, and that's what beta of T has to be in the dual. And we know that the optimal solution is going to have, in an optimal solution, the value is 0, so it's all going to work out that the beta of T is summed to 0. Now comes the important lemma. This is the lemma that we're going to use again and again to understand dual reduction and get deep insights and construct a new way of looking at general sender-receiver games. Given any dual solution alpha, so it's an optimal solution to the dual, alpha is an optimal solution to the dual, but mu is not necessarily an incentive compatible mechanism, it's just a mechanism. It's a mechanism possibly not incentive compatible. So it's a mapping from the profiles of types into probability distributions over actions, but it's not necessarily an incentive compatible mechanism. But given an optimal solution to the dual, we know that this is just Lagrangian analysis. The Lagrangian analysis is going to give us, in the usual way, that when you aggregate over how much, we're taking all of the incentive constraints, for each type, each sender, starting with each receiver J, you consider each action that he could be recommended to use, consider the contribution to his expected payoff from that, consider the contribution to his expected payoff when he deviates if he deviated to DJ unilaterally while everyone else is being honest obedient, multiply that by its Lagrange multiplier, then look at all the incentive constraints for the senders. For each sender I and each type TI, you ask what is he getting from the mechanism mu? And what would he get from the mechanism mu if he deviated to SI? If he planned to deviate to be SI when he's of type TI, well, weight that by its Lagrange multiplier. Take the lambda weighted sum of the deviations from the incentive constraints, and that will be equal to, by definition, the D's were constructed so that that is equal to the sum over all T's, the sum over all C's of what the mechanism gives you, the probability of the mechanism choosing C given T, times the aggregate alpha aggregated deviation value, the alpha aggregate deviation value with the action C and the types T. And all of that has to be greater than or equal to the sum of the beta T. Why is it greater than or equal to the sum of the beta T? Because we're taking, with your general mechanism, we're taking a weighted average of these Ds, but the betas are all the minimum. For any given T, you're taking the minimum. The betas are the minimum. So the weighted average, where mu is a mechanism, so the mu of C given T sum to 1 for every T. So we're taking a weighted average when we sum over C mu D. But the beta T is the smallest of those. But in an optimal solution to the dual, the beta T's sum to 0. So that tells us, what does that lemma say mathematically? It took me a while to read it to you. That tells us in words that if you have an optimal solution to the dual alpha, then for any mechanism mu, not necessarily incentive compatible, the expected net gains of unilateral alpha deviations from mu must always have a non-negative sum. So that's now you know everything about what dual analysis gives you. Now let's start doing dual reduction and use it. So I need to develop a little general notation. I just need to remind you of some basic ideas about Markov chains that you understand. What we have observed already, let me back up. What we've observed is that the dual variables of that are associated with our incentive constraints, these alphas, for the alpha J's for receiver J, those look like a Markov chain on the actions of receiver J. The dual variables of the incentive constraints for the sender I, those look like a Markov chain on the typesets of player I. Memorize that basic fact. If you haven't seen this paper before, if you didn't know the 1997 paper, then this is new to you. If you did know the 1997 paper, then the thing about the receivers is completely old, but the thing about the senders is the new part. We've got two collections of Markov chains. One, the duals give us Markov chains the two are essentially a collection of Markov chains on the typesets of the senders and the action sets of the receivers. Why are they Markov chains? Because they're non-negative variables associated with ordered pairs of types and actions. And then we've set it up so they sum to 1 in the appropriate way. What do you want to do with Markov chains? Well, there are two things you can do with Markov chains. And you've done them. So let me just remind you, I'll invent a little notation. So the top of this slide now is about general Markov chains. Take a set X, a Markov chain delta, which maps X into probability distributions over X. I'm going to here's new notation. X divided by delta, that denotes the set of minimal, non-empty, delta absorbing subsets of X. Why is delta absorbing? If and only if it's a subset of X. And for everything in Y, the probability of going to some X outside of Y is 0. So those are the absorbing sets. Find the minimal, non-empty delta absorbing subsets. And one thing you should know about a Markov chain is it partitions, I'm assuming we're talking about finite sets, it partitions the finite domain of the Markov chain into some things are some elements of X may be transient. They're not in any absorbing set, any minimal absorbing set, and then but there's at least one minimal absorbing set, and that minimal absorbing set is those minimal absorbing sets are disjoint, and they form a partition of the non-transient elements of X under the Markov chain. So I'm going to define psi and phi so that for any absorbing set, minimal absorbing set R is an X divided by delta that says R is a minimal absorbing set, and X is any point in X, then I'm going to define phi of x given r delta, that's the probability of x in the unique delta stationary distribution on R. You should know that on each of these minimal absorbing sets, there's a unique stationary distribution. And that's R phi dot R given R delta and delta. Now, psi of R given x and delta is the probability of a delta stochastic process reaching R from x. So I give you the equations below that the stationarity of phi says that the probability of y given R and delta is equal to the sum over, you can take it's equal to the probability under phi that you're at some other z, and then the probability that under the delta thing you go to y, and sum over all z's, that's going to still be the same as the probability of your being in y in the first place. That says stationarity, and of course the sum over the probability is going to be 1 for the elements of R, and it's only 0 for everything outside of R. That says that these are the stationary distributions on the minimal absorbing sets, and the psi, those are defined by well, let's see. If y is in the minimal absorbing set, that its probability of staying there is 1. If you're in another absorbing set, another minimal absorbing set that's different, then your probability is 0. And otherwise, the probability that you end up in R is the sum over all z's of the probability that starting in y you go to z, and then from z you go to R. Those equations define the psi. Okay. Now, the dual solutions, as I've told you, define Markov chains. The alpha i's are Markov chains on the types of sender I. The alpha j's for the receiver j's define Markov chains on the actions j. Let me just remind you, by the way, I'm going to go back a slide for a moment and just remind you that once you have the alphas, there's a formula that tells you what the betas are. So really, the alphas are the whole thing of the dual. The betas are a simple equation from the alphas. Okay, so the alphas are Markov chains. Given any optimal solution to the dual alpha, you forget about the beta. The beta is just generated from it for the game gamma. Let's define the alpha reduced game as follows. This is the big definition. It's gamma divided by alpha. Well, the set of players, the set of senders is the same set of senders, I. The set of receivers is the same set of receivers, j. The set of possible types for the senders is the minimal absorbing subsets under the alpha Markov chain. The actions for player I are the minimal absorbing subsets of CJ. These are going to be remember, these are going to be non-empty finite sets. Now, what's the probability distribution, and what's the utility function? So I have to tell you, first of all, what's the probability of having a profile of types in the reduced game tau? Well, each tau is a collection. What you take the summation. You take the summation over all type profiles in the original game, and then for each player I, you ask for each sender I, you say, if sender I were of type Ti, and then he keeps think of it this way: he keeps lying to himself about his type, and given his true type, he picks a new lie according to the alpha I Markov chain randomly. Then, given that, he tells a new lie given the alpha I Markov chain again. He keeps saying it again and again. Eventually, he's going to end up in one of the alpha I absorbing subsets of his own type, and he's going to stay there forever. The probability that he ends up there is the probability that his type is going to be tau I. His reduced type will be tau I. The players are forgetting their type information independently, so we multiply those together. That's the probability that they end up. So that tells you what the senders are doing is they're using their Markov chain to forget their actual type and remember only where they ended up in an infinite iteration of the alpha I Markov chain. Now, what's the payoff? Well, actually, all that matters is the gamma now is a profile of actions. Tau is of reduced actions. Tau is a profile of reduced types. The reduced types. So So this long equation for vk of tau gamma v sub k for player k of reduced actions gamma reduced types tau multiply. Forget about the divide on the right. Take it over and q. The probability of tau times the expected payoff must be equal to the following product of probabilities and types. The types are chosen according to the original game. The actions could be anything in the original game. The players are, as we said before, the senders are going to randomly forget their types and go to tau. And then once the gamma, those gammas, those are recommendations to the those are recommendations to the receivers to choose a particular recurrent minimal recurrent class in their alpha recurrent class in their action set. And what do you do in that? Well, you do a randomized strategy. The randomized strategy is the stationary distribution on it, the phi. So the players are going to actually, the player J is actually going to choose the CJ according to the stationary distribution on the gamma J minimal absorbing set that he's been told to go to, the alpha J stationary distribution on that minimal absorbing set gamma J. So that's what the senders are forgetting their types according to their alpha I. The receivers, once they're told a minimal absorbing set, once they choose, what they're going to do with that is if they obey a mediator's recommendation to do so, they are going to be randomizing according to the unique stationary distribution on that set. Then they get their payoff, and that's it. That's the reduced game. Wow. Let me just observe. Any mechanism on this reduced game would be a function, a lambda mechanism. It's going to be a function from the profiles of reduced types for the senders into probability distributions over the reduced actions. Here's the big theorem. Let me just say, first of all, what are we? We've just had a little tour for about half an hour where I've taken you through linear programming in sort of the obvious way that if you should have learned in first year graduate school if you were studying optimization theory. And we've then done Markov chains in the obvious way, which in first year graduate course you'd have. And I've just followed my nose through it all. And we're in game theory. The question is, have we done anything that's game theoretically interesting? The mathematics is so nice that if we find a pony here, it must be pretty good. But let's see if there's a pony with all this stuff here. Well, the answer is theorem. If alpha is an optimal solution to the dual solution for gamma, then any incentive compatible mechanism for the alpha reduced game induces, in the obvious way, a incentive compatible mechanism for the original game. What's the obvious way? What's the induced mechanism from a given lambda, which I'll denote by mu super lambda? Well, given a profile of types T, and a profile of actions C, what's the probability with the types T you would go to action C? Well, you might have it. I don't know what profile of reduced types you're going to have. Call it tau. That could be any of them. I don't know what profile of actions of reduced actions is going to be happening in lambda. Call it gamma. But we'll take the probability of the probability that given T, you end up with this psi term. This product of psi's gives us the probability that the senders are going to, under this contrived alpha forgetting, they're going to forget the detailed information of types, but only remember their reduced type. Then, given that recommendation, the mediator is going to recommend the gamma reduced actions, and then the receivers are going to play their stationary distributions, are independently going to play their stationary distributions on the reduced actions that have been designated for them. And now the big result is that if lambda is incentive compatible in the reduced game, then mu lambda is also incentive compatible for the original game. So that tells us that by analyzing the reduced game, everything we do with incentive compatible mechanisms, everything we do with Nash equilibria of any game with communication is going to ultimately yield something which is a Nash equilibrium of the corresponding game in corresponding original game. We might be throwing away some things. In that sense, we're refining the set of equilibria, but we can analyze the reduced game and everything we get will make sense for the original game. Now, the second fact, this should excite you, is that for any finite game, iterative dual reduction yields an elementary reduced game. Why is that? Give me a game gamma. find an optimal solution to the dual, any optimal solution. You'll get a reduced game. There's only one case where the reduced game doesn't change anything. That's if all the alphas for non-trivial incentive constraints are 0. If any pair of types or pair of actions, the distinct pair of actions or distinct pair of types has a non-trivial reduced Lagrange multiplier, then we're going to have the reduced game is going to have strictly fewer. Those linked actions are going to get tied together. Either one of them is transient, or they're going to be tied together in a minimal absorbing set. And so we're going to have strictly fewer types or actions in the reduced game. Let me just, there's one important thing I forgot to tell you on the previous slide. Non-trivial solutions with some alpha k strictly positive and for a distinct pair of types or distinct pair of actions, depending on whether k is a sender or a receiver, non-trivial dual solutions exist if and only if gamma is not elementary. So if you have if you have a game which is not elementary, then you can always find a non-trivial solution. How do I know that? Because in linear programming, you can always find a solution to the dual for any incentive constraint. You can for any constraint in the primal, you can find an optimal solution to the dual where that constraint has a strictly positive Lagrange multiplier or dual variable. You can find that if and only if that constraint is always binding in the primal solutions. So that's a basic fact of linear programming. And therefore we can if our game is not elementary, then we can find a non-trivial dual solution, and we'll get a reduced game which has strictly the sum of this. You count how many types do all the senders have, and how many actions do all the receivers have, at least one for each of them. Add them all up. That's how big the game is in some sense, and we'll get a strictly smaller game if every time we do dual reduction. These are non-negative integers. They can't go below 0 because you have to have at least one action each type for each player. So you can keep reducing it until you hit an elementary game. And our theorem says in each of those iterative dual reductions, the incentive compatible mechanisms you're inducing become incentive compatible mechanisms for the previous one. And you can iteratively apply that back to the original. So iterative dual reduction can reduce any game to an elementary reduced game. That is the big theorem. This was proven in 1997 for general strategic form games, and now we've learned how to do it for sender-receiver games where we have informational incentive constraints as well as the strategic incentive constraints. Time is late, so I should do some examples. The proof is, I should mention these notes are on the web, and I will close by reminding you of where they're on my website. And the proof is in these notes. I think I will skip it for now because time is short, or I can come back to it in a bit. Let me look at it for a moment. I think I can say this. For the receivers, the main intuition is when everyone's playing according to the dual reduced game, then for each player who's playing according to the dual reduced game honestly and or obediently, applying the alpha deviation does nothing because of the stationarity for the receivers, because they've already of the forgetting property for the senders. So what we have to ask is, what if a player were to use his type information if he's a sender to choose a different report? What if a player were to choose a specific action rather than a reduced action, and to have to show that those are not valuable? And the way you do it is, well, let me talk about the receivers first. If one player could benefit by deviating from the mechanism mu lambda and choosing a different action, one receiver, then he'd do even better by applying the alpha, that receiver J would do even better by applying the alpha J Markov chain to it once, because applying the alpha Markov chains to the other guys doesn't do anything because they're stationary or they've forgotten their type, and because of the stationarity or forgetting properties of the reduced game, and the other players are playing according to the reduced game. And this guy must be gaining, must be doing even better when he plays alpha. Apply alpha again and again, you're going to eventually, and then average where you get in all those different alphas. That's going to be ultimately where you get in the long run stationary distribution of the alphas by the what is it called, the ergodic theorem. And that was something he could have done anyway. But we assumed it wasn't an equilibrium for him to deviate to one of his reduced game things in the original game. We had set of compatibility in the reduced game. For the receivers, it's a little trickier, and staring at the definition of the reduced game, there's something that should have led me to almost throw this whole paper away, but I'm not throwing the paper away because it's not a problem. The payoff function tau is an aggregate across different types of taus, payoffs. We've forgotten what our type is, and we're averaging them. But wait a minute, guys. The original game, if I rescaled one of the types payoffs by multiplying it by 100 and leaving all the other types payoffs the same, that would certainly change the average payoff for one of these reduced types. So what's going on? Is this game, if this analysis, the equilibrium analysis had better be invariant under that kind of transformation of the original game? And the answer is it is. Let me actually say, instead of proving to the incentive compatibility for the senders, which is straightforward, I'll simply state a different theorem, which is consider any dual solution, for any dual solution alpha. Alpha is an optimal solution to the dual for gamma. Consider any sender, consider any tau who's that's one of the reduced types, and consider any Ri, which is one of the types in the set, of the original set, in this minimal absorbing subset of Ti, alpha absorbing subset. Consider two mechanisms for the reduced game, lambda and eta, that don't depend on I's reduced type. That's what you get when I make some report to the mediator and then shuts up. That's all he has to do is so just the lambda and eta represent two different things that could happen in the reduced game mechanism after I has reported his type. Supposing type Ri prefers, weakly prefers lambda over eta, then for any other type that has a positive probability of coming into the tau I, that reduced type must also have the same weak preferences. So this is a basic fact that says that our dual solutions are in fact basically giving all the types the same incentives within the reduced, where they make choices in incentive compatible mechanisms, in mechanisms that are incentive compatible for everybody else in the reduced game, and that the only thing that's a little tricky is the transient types that aren't in this set tau I, but that forget when they forget into it. They might be indifferent among everything. They might have more indifferences, but all the types that are inside corollary that they can all map to each other, and they must have exactly the same preferences over the essential mechanisms. And that's the proof is in this slide 6. I'm going to skip that because I want to give you, I should say something about some examples. In the 1997 paper, I observed that games like the Battle of Sexes game, those are elementary games. Take a 50-50, a mechanism that randomizes 50-50 across the diagonal. That satisfies every incentive constraint strictly, no dual solutions. The prisoner's dilemma, or this one that has a weak, an imperfect equilibrium at the dominated, the defect, what is that, DD? I'm sorry, it's a weak equilibrium at the cooperate, but it's an imperfect equilibrium. There's the bad equilibrium. But the CIs are dominated by the CJs are dominated by the DJs. Basically, the incentive constraints, dual solutions include mapping from the cooperate to defect for each player, and the reduced game just eliminates the dominated actions, the weakly dominated actions. So we eliminate that weakly dominated equilibrium. It's Pareto superior, but it's weakly dominated actions. For this is essentially a constant sum game, and I noted that it turns out that the dual solutions, the dual solutions essentially are going to give us a alpha stationary strategies of the dual solutions are the unique equilibrium of this mixed game. So the dual reduction of a two-person zero-sum game is essentially going to be choose the min-max strategies. The min-max strategies are the reduced game strategies, and everything else goes away. This is an interesting game. Let me back up for a moment and say, here's a game with a sender and one receiver that's sort of interesting. I won't say much about it. Basically, forget about the bad type on top. Ri at top is a bad type. At the bottom, there's something important to talk about. Both the sender 1 and the receiver player 2 both want to, they'd like to use the sender's information and go to B or A if it's S, and T or C or D if it's D, C or D if it's T, if the type is T. And of course, they'd like to go to the extreme ones that get the 9s rather than the 8s. But the bad type really likes the extreme actions and hate. But when the sender is bad, then the receiver doesn't want to go to the extreme actions. The sender prefers to do the more moderate actions. And so what's interesting here, I've given enough probability if either one of these types, S or T, was successfully getting the receiver to go to the extreme action, then that's the type which the receiver would want to imitate. So that can't happen. The three types are equally likely. And it turns out there are multiple dual solutions. The R's map onto the R maps, but with at least 1/3 weight on each of the two. The bad type maps to the two good types with at least 1/3 of its weight on one of them, and up to 2/3 on the other. And the extreme actions map to the respective moderate actions, but there are multiple reduced games. Let me talk about this. This is a version of Shapley's game, which is famous, a 3x3 game that has a unique Nash equilibrium, 1/3, 1/3, 1/3 for each, but it also has a correlated equilibrium where you avoid the diagonals and have 1/6 probability on each of the Pareto superior correlated equilibrium. The correlated equilibrium that randomizes uniformly over the 6 non-diagonal elements satisfies 6 incentive constraints strictly, and so it implies that every dual solution must have 0 Lagrange multipliers for the dual variables, which are basically the counterclockwise ones that are strict here. But this game is not elementary. It has a dual solution where the clockwise directions have positive Lagrange multipliers. So the dual reduction is a 1x1 game where each player's only option is to randomize uniformly over C, D, and E, yielding, and the expected payoffs, of course, a third. So dual reduction suggests that the correlated equilibrium described above may be imperfect in some sense. In small print here, I note that if you change those 0 zeros on the diagonal to any epsilon, you would this interesting case, which I'd call this is a case of non-transitive dual solutions. It's a non-transitive dual solution in the sense that you can get a positive Lagrange multiplier from C1 to D1, and you can get a positive Lagrange multiplier from D1 to E1, but you can't get a positive Lagrange multiplier from E1 to D1 directly. Let me tell you an important theorem that I didn't know before this year. I'm sorry, I'm almost out of time, but please let me persist in this because this is a new result and I have never presented it to anyone before. For any game, the games with transitive dual solutions, for any game gamma, we can say the dual solution alpha is maximal if and only if its support is maximal among all dual solutions to the game. And by the way, take 2 dual solutions and take the average of them, you'll get a new dual solution which has positives in each of the ones where either one of them had positive non-trivial components. So we want to have its maximal support. We may define the dual magnitude to be the number of non-zero, non-trivial components in a maximal dual solution. We may say that a game gamma has transitive dual solutions if and only if in any maximal dual solution for any player who could be a sender or receiver, and for any three of the player's alternatives, x, y, and z, if there's a positive Lagrange multiplier if you can have a positive Lagrange multiplier from y to x, that means and you can also have a positive Lagrange multiplier from z to y, then you can have a positive Lagrange multiplier from z to x. That's transitive. Now, obviously, we could fix everything about a game except for the utility functions. I'll call that the framework for the sender-receiver's game. So once I've fixed a framework for any utility vector u, I'll call it gamma of u. That's the game that's generated. Let's assume that the p distribution has full support. That is to say, all profiles of types have strictly positive probability. We've seen, I just showed you an example of a 3x3 game which did not have a transitive dual solution, but this failure of dual transitivity is very sensitive to small changes in the utilities. Claim, given any framework, everything about the game except the utility function with positive support, with full support on the probabilities, then the set of utility functions u, such that gamma of u, the resulting game, has transitive dual solutions, that set is dense in utility space. And let me just sketch the proof a little bit. Take any non-empty open set in utility space. Let's find a utility function so that gamma of u has a dual magnitude that's minimal in the set. If it's elementary, it'll be dual magnitude 0. How can you minimize? I'm minimizing over an open set. Am I allowed to do that? Yes, I am, because these magnitudes, the magnitude is the number of non-zero, non-trivial components. That's a non-negative finite number. For every point in the open set, you have a non-negative finite number. There's a minimum. There are finitely many possible values. Among the finitely many possible values, there are one is smallest. So even over an open set, this is not a continuous function, but it is a finite range function, and therefore it does attain its minimum even over an open set. Then we can show that this gamma of u with locally minimal dual magnitude will have transitive dual solutions, and I'll show you how you perturb it. Basically, you just have to find if gamma of u does not have transitive dual solutions, then either some receiver has three actions that violate transitivity, or some sender has three types that violate transitivity. And the way we do it for any arbitrarily small epsilon, we're going to construct u hat to be the same as u, except take the action. There's this action di such that di is the middle from c. C always wants to claim to be d, and d always wants to claim to be e, but e sometimes strictly prefers in a maximal dual solution. It says ei sometimes in some incentive compatible mechanism strictly prefers doing c than doing e. But I'm sorry, this says no. This says this, yeah, 0. Then we can construct. We're going to construct this. I'm sorry, I said it wrong. This says that in all dual solutions, when you're told to ci, you're willing to do di. In all dual solutions, when you're told to di, you're willing to do ei. But we don't know that now in this one here, we can construct u till to be the same, except there's going to be some small epsilon probability that when told to do di, player I is going to deviate to the ei according to some other ei according to the alpha ej rather, according to the alpha deviation, alpha Markov chain, alpha j Markov chain. That's in J's payoff. He's not really doing that as far as the others are concerned, but for his own payoffs he is. We're just changing J's utility function in the case when he's when he's told to do dj. It's going to be as if when he's told to do dj, he sometimes does some other ej according to the alpha in his own payoff. For case 2, it's going to be, we're going to construct something. So for player I, when he thinks he's type si, he's going to think that there's an epsilon probability that what he did was he lied to himself according to his Markov chain, and then believed the lie rather than the original truth. That's just in his mind, not in anybody else's. But these perturbations turns out define a game which will have which the intransitivity goes away, and we'd have a strictly smaller set of positive dual variables, and we'd have to lose one of these positive dual variables, and therefore we'd have strictly smaller dual magnitude. But by construction, we were assuming that the U was minimal. So let me stop there. I'm over time. I apologize.
Thank you very much.
1 hour. This summarizes, most importantly, in the bottom of the slide, that's the URL where these notes are. Here's my abstract. I'll just simply say in conclusion, dual reduction identifies incentive constraints that are hard to satisfy with strict perfection. It models them as inseparable alternatives in a reduced game. Iterative dual reduction of all such inseparable actions and types yields an elementary reduced game in which all incentive constraints can be satisfied strictly. And thus, dual reduction allows us to analyze games without any of the knife edge imperfect equilibrium issues, because any such issues in the original game have been identified and have been embedded into the structure of the reduced game. Sorry.
Thank you very much. It was a fantastic talk.
It's the end of your day, your work day in Budapest. It's morning here. I'm happy to stay and talk, but it's socially acceptable to say goodbye. Thank you.
Wait.
Roger. Thank you very much for joining us like this, and thank you for the extraordinary results and exposition. I do have one quick question, and it's an educated guess. So take Crawford-Sobel uniform quadratic and discretize it, and make the preference difference enough so that there are genuinely multiple equilibria. It's my guess that there is an incentive compatible mechanism of the type you characterized for each of the, in other words, that it doesn't resolve the substantive multiple equilibrium problem, even though you've got a framework that resolves the ambiguity of language multiplicities. The substantive multiple equilibrium problem seems to still persist. Is that correct? You can say no.
The short answer is I don't know. I have analyzed discrete cases of Crawford-Sobel in, say, uniform distribution, uniform quadratic. What I've not done is analyze the duals, which of course I know I've analyzed certain optima. I can say that the whole point of Crawford-Sobel, the original paper, was that as the bias got smaller, the equilibrium set got smaller also.
Larger.
And a certain amount of inevitable clumping happened, certainly when the bias, we'll call it bias parameter B, that's what I called it last time I studied. Maybe that's in the original paper or not, I don't know. But as that bias parameter B gets smaller, so that the receiver's payoff is ideal, is more similar to the sender's, we might find that the reduced game, that there are inseparable types, and they may induce inseparable actions. I honestly don't know. Certainly, if you could find a incentive compatible mechanism where all incentive constraints were sort of strict, it's a continuous, to look at the continuous limit, then probably that's not going to be a problem. But I think it was of the nature of the example that when the bias got small, it was really hard to do that because of the interactions between the sender's incentives and the receiver's incentives was intrinsic to everything. The analysis of this game with a mediator is fundamentally different from the analysis of your original paper, which was about unmediated communication. And that unmediated communication, in general, in my mind, it makes things more complicated. So it was really terrific that you actually got results from that. But
the commitment assumption is a little different because of the mediator.
Because the mediator, yes, the commitment assumption is exactly the same. But the mediator gives us more flexibility. The mediator, it has been learned, and now let me see if I can remember who has been published. Whoever has published the papers on this is welcome to grab the mic next and remind me, because I remember your papers, but I've forgotten. I'm not retrieving them in my mind fast enough. people have shown that adding mediators changes the analysis. But my guess is that things get interesting, that things might get dual reduction interesting. Well, let's say things are dual reduction uninteresting if the original game is elementary. My guess is that when the bias is small, we might have we might start having non-trivial dual reductions, which is saying that there are various restrictions on communication that can be supported robustly in equilibrium. And if we're eliminating some equilibria, we're identifying them perhaps as being, quote, imperfect, if this is a theory of refinement of equilibrium in the broader mechanism design context.
Okay, thank you very much.
Thank you.
We're grateful, and we now have something to think ourselves to sleep with.
I am
that we didn't have this morning. So
it's all on the web. It's not featured large on my research page, but dual reduction 2023 or something like that is a title somewhere that can be clicked on, or that URL is there. It's on my research page, and tilde R Meyer home Chicago edu tilde R Myerson research L dual reduction L dual 2023 notes. The notes were first written in 2023, but the result on transitive the denseness of transitive dual solutions is a new result this year.
Okay, thank you. Thank you.
Thank you. I'm so sorry to see you only remotely on this little screen, but it was wonderful to see you, Vincent, and everyone else there. Thank you for inviting me to this important conference. I'm sorry that I couldn't get there.